Hello and welcome to Equity Education, the chemistry version, and today we're going to be looking at the chemistry of benzene. Okay, so we're going to learn some reaction mechanisms in this video, and well, I hope it's useful, but now I'd like you to open up your booklets and we will get started. So, chemistry of benzene. So, the benzene ring is an important part of many organic compounds, some of which are shown below. So we have TNT, paracetamol, aspirin, and TCP. Okay, so I'd like you to just see if you can work out what these uses are and see if you can work out what some of the functional groups are in these molecules. Okay, so I reckon most of you know that TNT, toluene, I can't say it, is used as explosives, and the word toluene is the old name for benzene with a methyl group on, so methyl benzene. That's where this name comes from. The functional groups, so we have nitro groups, and obviously we have benzene. Paracetamol, I'm sure you've guessed, is a painkiller. And we have something here, so this benzene with an OH group attached is actually its separate functional group. We call this phenol, and here we have an NH bonded with a C double bond O, and we call this an amide link. An amide link. We'll be doing some more videos and some more work on phenols and amides in the future. Okay, aspirin again is used as a painkiller and could be classed as an anti-inflammatory, so I'll write it down. Functional groups, so we have a carboxylic acid group up here, which you should know. Oh, I haven't got much space here. So carboxylic acid, benzene, and we have an ester link here. Again, if you're unsure what esters are, have a look at the ester video. And we also have TCP, which is used as an antiseptic. You might have some in your house. It's usually what hospitals smell like when you have to go. Unfortunately, when you have to go, I quite like the smell. Lots of people don't. And again, our functional groups are benzene and, oh no, benzene, we have, excuse me, we don't have benzene because we have that thing we talked about earlier. So we have a benzene and an OH attached to it. So this is phenol, and then we have a chloro group as well. Okay, so moving on. So benzene does not undergo electrophilic addition reactions. This is because the pi delocalized electron ring stabilizes the benzene. It does not have the electron charge density to polarize any molecules approaching it, and I'll just stop there. So if you're unsure about what I've said here, just watch the previous video on benzene and that will explain it. Okay, so benzene does undergo, so it undergoes electrophilic substitution reactions, whereby an electrophile has to be generated in situ with benzene by using a catalyst. Okay, in situ just means along with the benzene. Okay, so electrophilic substitution reactions. So all benzene electrophilic substitution reactions follow the same general equation, which are C6H 6, which is my molecular formula for benzene, plus X plus, which is my electrophile, form C6H5X, and we have removed a H plus. Obviously it's substitution, yeah, because we have removed one H plus and replaced it with our electrophile. Okay, so you have to know these reaction mechanisms. You also have to know the reagents and conditions for these reactions we're going to go through. So the first one is nitration. So nitration is the addition of a nitro group or NO2 plus group to benzene by removing a H plus, or dependent how you look at it, you might also see it as a hydrogen atom. Yep. Okay, so it's a bit of a debatable which book you look in when it says a H plus or hydrogen atom, so I'll put both down. Right, so the overall equation is my benzene C6H6 plus nitric acid forms C6H5NO2 plus H2O. So I have added a nitro group to my benzene ring, hence why it's called nitration. The conditions, so we need 50 to 55 degrees temperature, and we need concentrated acids. The reagents, we need concentrated nitric acid. The catalyst is concentrated H2SO4, and you have to remember all these, okay? Yeah. And our nitrating mixture. So our nitrating mixture is concentrated HNO3 plus concentrated H2SO4. So I've mixed my two acids together. And the temperature must be kept below 55 degrees Celsius to stop multiple substitutions. So if we go above 55 degrees Celsius, maybe we get more nitride groups added than we want to. Okay, so let's carry on. So generating the electrophile, remember that this is our overall equation, our general equation, and we need to generate this X plus to add to our benzene. Okay, so how does this happen? Well, we mix the two acids together. So H2SO4 plus HNO3. And what happens is, because sulfuric acid is a stronger acid than nitric acid, the sulfuric acid will donate a H plus, and the nitric acid will accept a H plus. So in this instance, even though they're both acids, nitric acid is actually acting as a base, and sulfuric acid is acting as an acid. Now obviously H2NO3 plus is unstable, so this breaks down to produce H2O plus NO2 plus. Okay, now I could write this as an overall equation, however I'm just going to leave it as the two separate ones. So now we have generated our electrophile. Right, the mechanism. So the mechanism is called electrophilic substitution, and the name is nitration. Okay, so what happens? So we have our benzene knocking around, and our electrons from our pi delocalized electron ring are attracted to our positive electrophile. This means that a dative covalent bond between the nitro group, the electrophile, and the benzene happens. But that also means then that we break this pi delocalized electron structure. And because we've removed 2 electrons to form this bond, we have a positive partial delocalized electron ring. Now to reform this ring, we take the electrons from the H to C covalent bond and put them back into the ring, and therefore I have substituted in a nitro group and I have taken out a H plus. Okay, pretty simple so far. Yeah, you have to remember this in detail though, don't get these things wrong. So what role does sulfuric acid play and how can this be shown? Well, I'll let you have a think about it and then we'll go through it. Okay, so probably gave you a big hint in the reagents at the start, because we said that the sulfuric acid is a catalyst. Now we know from the definition of a catalyst that, well, depending on our definition, we know that the catalyst does not get used up in the reaction. So here we have HSO4 minus. Well, it looks like it has been used up, but what actually happens is that we can reform the H2SO4 because we have a H plus left over here. So we reform the catalyst by using our H plus, which has been substituted out, to produce H2SO4 again. Therefore it has not been used up in the reaction, so it acts as a catalyst. Alright, so I'm just going to write this down because I explained this while I was doing the mechanism. So what happens is, so the first stage, so the pi delocalized electron ring breaks to form a dative covalent bond with the electrophile. In this case it's NO2+. The intermediate has 4 electrons spread over 6 carbon atoms. The electrons from the CH covalent bond move into the partial pi ring to reform the ring producing a pi delocalized electron system. Okay, we're just going to look at our mechanism and explain these 2 points. So step 1, the pi delocalized electron ring breaks to form a dative covalent bond with the electrophile. We can see this happening here. Remember, there's 6 delocalized electrons in this ring, yeah? So we formed a dative covalent bond here. The intermediate has 4 electrons spread over 6 carbon atoms. So here, this is important. You have to make sure, over 5 carbon atoms. Let's get it right. So it's spread over 5 carbon atoms. So 1, 2, 3, 4, 5. Which means that your partial pi delocalized electron system needs to be showing that it's covering these 5 carbon atoms here. And because we've removed 2 electrons, we're going to have a positive charge in the middle. And then the electrons from the CH covalent bond move into the partial pi ring to reform the ring, producing a pi delocalized electron system. And we can see that happening here, and we've removed a H+, hence it is substitution. Right, so that's the first one that you need to know. So we're going to move on to Friedel-Crafts reactions. So benzene can undergo 3 types of Friedel-Crafts reactions, these being halogenation, alkylation, and acylation. And all of these follow the same principles. So the general reaction can be written as, I have my benzene, my RCl. I'm going to make that slightly bigger because I'm going to have to write over it. So I have replaced my R. So I've taken this R, I've put it onto the benzene ring, I've removed a H plus by doing this, and that's where this H comes from. So I form HCl here. And I need to reflux in presence of an ACl3 catalyst. This could be an FeCl3 catalyst as well. I'll talk about that in a little bit. But you must also have anhydrous conditions. Okay, so we also need anhydrous conditions. Right, so I'm just going to let you look at that reaction for a little bit, and I'll be back in a second. Okay, so we will carry on. So they are all, excuse me, they are all electrophilic substitution reactions or mechanisms, yeah? Okay, so the procedure for the three reactions follow the three steps outlined below. So for halogenation, alkylation, acylation, we always do the same three steps. So step one is to the generation of the electrophile using a halogen carrier. The halogen carrier is either aluminium chloride or iron chloride. You could have different ones, but these are the two most popular. It is used to produce the electrophile. So what actually happens is we take our RCl, we add, I'll stick with aluminium chloride to it, and we produce R plus AlCl4 minus. The reason why this happens is because the AlCl3 polarizes the RCl due to high electronegativity. Okay, so here the chlorine is high in electronegativity, and this is chlorine as well, so it pulls the electrons from this bond here and breaks it to form our electrophile. Okay, step 2. So in step 2 we have electrophilic attack of our electrophile on the benzene ring. And finally, step 3 is reforming the catalyst. Okay, right, so these are all going to be very similar, okay? But we need to go through all of them. So halogenation. So halogenation, our first one. So our overall reaction is we have benzene, excuse me, plus Cl2 to C6H5Cl plus HCl. Conditions: warm, reflux, and remember, anhydrous. The reagents, chlorine, depending on which one we are talking about, the halogens might be bromine as well, mixing with the benzene obviously, and the catalyst is a halogen carrier, AlCl3 or FeCl3. Formation of the electrophile. So we talked about this previously. So to form the electrophile, we have aluminium chloride. We break this covalent bond here to form our electrophile. And then we have our mechanism, and our mechanism is exactly the same as our nitration. So Cl plus, our pi electron delocalized system breaks. We now have 4 electrons spread over 5 carbon atoms. The electrons from the CH covalent bond go back into reform the benzene, the pi delocalized benzene ring, and then we have the H plus removed or substituted. So exactly the same thing as nitro, but we've added a Cl instead. How do you think we regenerate the catalyst? Well, we have this H plus left over. We've produced ACl4 minus, so ACl4 minus plus H plus produces ACl3. So it hasn't been used up in the reaction, and we've produced our HCl, which we can see in our overall equation up here. Okay, so that's halogenation. Okay, alkylation. So moving on. Why do we do it? So it's used to add an alkyl chain to a benzene ring. Therefore, the carbon chain length, which is useful, increasing the carbon chain length, which is useful for making other products. Remember, when we're talking about an alkyl chain, that means alkyl is a representative of an R group, so CH3, CH2. Yeah? Okay. Our overall reaction. I know I'm going through this quite quickly because it's all very similar. So, our overall reaction, C6H6 plus CH3Cl. So this is our R we use in our general equation above. Unsurprisingly, we're going to add that on. Don't know what's happened there. Let's get rid of that. Plus H, what are we going to have left over? HCl, obviously. Conditions: warm, reflux, anhydrous. Reagents: CH3Cl, or whatever RCl is, because it could be CH3, CH2. Catalyst, again, ACl or FeCl3. Formation of the electrophile. I'm going to let you have a go at doing this because I reckon you'll be able to do it now. Okay, I'm sure you've all come up with this. So again, it's very similar to our example we used previously. So our generating our electrophile is the CH3+. We have the FeCl4- made over, and again, your turn, you're going to do the mechanism on your own. Okay, so I'll give you a couple of minutes. Okay, I'm sure you've all got something that looks like this. So pi delocalized electron ring breaks, forming a dative covalent bond with our electrophile. We then put the, so then we have 4 electrons spread over 5 carbon atoms. So the electrons from our HC covalent bond go back into the ring to reform our pi delocalized electron ring, and we have added on our CH3 and removed the H+. Again, your turn to do this. Regenerate the catalyst, have a go. Okay, and I'm sure you've all got this. So H plus FeCl4 minus forms hydrochloric acid plus FeCl3, or HCl plus FeCl3. Right, okay, so last one, acylation. So what is acylation? Acylation is used to attach what are we attaching? It is used to attach an ketone group, and this can be converted into other useful functional groups, such as, well, we can have lots, maybe alcohol, maybe carboxylic acid. And I'm gonna change this here, because strictly let's write acetyl bond O, because it will form an aromatic ketone rather than a ketone group. Okay, so our overall reaction, C6H6 plus CH3COCl forms C6H5, C double bond CCOCl plus HCl. Sorry, I just made a mistake there. So C6CH5Cl. And have the Cl here. We have the CH3. Okay, so bit of housekeeping. So this is ethanoyl chloride. It's an acyl chloride, yeah? And I have another video about acyl chlorides if you're unsure what this is. So what we've actually formed here is also an aromatic ketone. And you'll see the structure a bit better once we do the mechanism below. Well, actually, you're going to do everything else on your own now. You should be able to fill it out from all of the information we've used previously. Okay, so look back on your notes and you should be able to fill all of this out. Okay, let's see how you got on. Sure you managed to do this. So conditions are all the same as our previous two. So warm reflux anhydrous. Our reagent is CH3COCl in this example, but remember it's just RCOCl. Catalyst, we're either going to use AlCl3 or FeCl3. Forming the electrophile, so I'm going to form this as my electrophile, CH3CO plus HCl, and this is my mechanism. Okay, so it's all exactly the same. So lots of students find it difficult, find the acylation more difficult than the halogenation and the alkylation, but they're exactly the same. As long as you follow the same patterns, you shouldn't be able to get lost. Okay, and a side note, when I was saying about an aromatic ketone, so this is an aromatic ketone, so it has the benzene and it has the C double bond O in the middle. Remember, that's what our ketone structure looks like, with the C double bond O in the middle. And we regenerate the catalyst using this formula. Okay, so I hope that was useful. Pretty quick today because all the mechanisms were generally the same, and yeah, as I say, hopefully it was useful, and I will see you next time. Okay, bye bye.